This video contains the solutions for numbers 30 through 32 on your Practice AP Physics C test. Number 30, a certain spring is stretched by an amount x. It produces a restoring force. So they're giving us force as a function of x, where a and b are constants. How much work is done by an external force in stretching the spring by an amount d from its equilibrium length? Well, I think we just did this a couple problems ago. I know that work, this is number 30, work is equal to the integral of force as a function of x dx. Remember, in the simplest situations where force is constant, then work equals force times distance. But if it's a variable, then we have to take the area under that curve. It's got to be a function of x to do this, right? If it's a function of time, then this integral would mean something else. It's impulse, or a change in momentum. But here we have our force as a function of x, so we're moving it from 0 to d. So minus ax plus bx squared dx. Let's find the antiderivative of that. That would be minus a over 2x squared plus b over 3x cubed from 0 to d. So I just have to plug the d's in here. It'll give me minus a over 2d squared plus b over 3d cubed. Let's see what that looks like. No, and no. Well, it kind of looks like this, but the signs are backwards. So how can we convince ourselves that that's okay to pick this one? And we can convince ourselves because they said it's stretched by an amount d from its equilibrium length. They didn't say, they didn't tell us anything about which direction was what. So I think that since work is opposite, the work that the spring does is opposite in direction. The work that the force does is opposite. So if we're just talking about magnitudes here, I think that we're correct to say that this is the same as this, because positive work, negative work, it all depends on your choice of direction. So that's the opposite in sign, but it is the correct answer. Number 31 and 32 both refer to this situation. We have a static equilibrium situation. A ladder makes an angle of theta here. The weight of the ladder is W, according to them, and that force, that's mg, right? mg is the same as weight. So that force acts at the center of mass, and let's just call the length of the ladder L. Right, so that would act at L over 2. What other forces are there? Well, they say that there's friction between the ladder and the floor, so there'd be a normal force here, and then a frictional force. If there were no friction, the ladder would slide like that down, so that means the frictional force must be this way, holding it in place. You call that Fx and Fy, like we did when we did this kind of problem. And then the wall is also pushing back on the ladder here. And they told us that the friction up here between the ladder and the wall, that's negligible. So we'll call that the force of the wall. All right, so static equilibrium. The rotational point that we should pick here is the one that has the most forces acting on it, because those will be out of play, right? If we do net torques, if I pick this rotational point, the radius would be 0, so I don't have to consider those at all. So this will be my rotational point. And I know that the net torque and the net force on this must be 0. This must be equal to W, because net force is also 0, and those are the only two vertical components. And these must be equal to each other. And what do they want? They want the magnitude of the normal force exerted by the floor on the ladder in number 31. Well, that's this force. And since all the forces, the net force must be 0, then this has got to be the same as this. So 31 Fy is equal to W, and that's answer choice A. Excuse me. Number 32, not as easy by a long stretch. So let's see if we can do it. This is where we have to use net torque. There are two torques, and since it's not moving, it's in static equilibrium, those two torques must be equal. Well, let's see what those torques are. Torque is equal to force times radius times the sine of the angle. So let's see if we can do that for these two. This force is W. The radius is half the length of the ladder. And the angle here, it's actually not theta, right? It's the complement of theta. So that would be 90 minus theta. And that's got to be equal to the other torque. Those are opposite interior angles, so that is theta. So that's the force of the wall that we're looking for, times the radius is the full length L, and sine of theta. All right, now we're pretty close, but you notice that none of the answer choices have anything about a 90 minus theta. So we have to do a little bit of trig identity, or try to figure out what's going on here. There's a couple ways to get there. One of them is just to realize that the sine of an angle in a right triangle is the same as the cosine of the other angle in the right triangle, right? Because all you're doing, if you switch from this angle to this one, is switching your perspective on who's opposite and who's adjacent. So the sine of this angle is opposite over hypotenuse. But the cosine of this angle is adjacent over hypotenuse. So the sine of this is equal to the cosine of theta. Okay? If that seems like a little too intuitive, like you might not think of that, well, what else could you do? You could use the sine angle sum formula, or the angle difference in this case, which says that that's sine, remember it's sine cosine minus sine cosine, so that's sine of 90 times the cosine of theta minus, and then you switch the places of those, cosine of 90 minus, times the sine of theta. And cosine of 90 is 0, so this term drops out. Cosine of theta, sine of 90 is 1, so that also gets you cosine theta. I like the geometric way of getting there better. So anyway, that gives us now W times, the L's on both sides cancel out, just have a 1/2 here, and the force of the wall, what we're looking for, times the L's canceled out, times sine theta. We're trying to find this, so I'll solve for that. Divide over the sine, that gives me W over 2 is cosine theta over sine theta, and cosine over sine is cotangent. So the correct answer is E, W over 2 times cotangent of theta.